We are starting, good job, lesson 7.1 today as we start into chapter 7, which is going to take us a different direction, okay? We're no longer talking about radicals and square roots. We are leading into logarithms, okay? But we're going to start here in lesson 7.1 talking about exponential functions. And I know, before you start complaining, yes, we are starting with graphs. But we're going to get those graphs done, and then I think we have graphs maybe the first 2 lessons, and then we get past the graphs. So, do you guys know what an exponential function looks like in terms of a graph? Not a straight line. It's a gradual curve at the beginning and then goes exponentially up. I think your curve was upside down, though. I think you were curving the wrong way. You, Jaden. I think. I'm backwards from you and all that. But, okay, so now, and a lot of you just kind of gave me this look like, yeah, I don't really know, or you don't want to answer me. But, and here's what it's going to come down to. If you're not sure of what the graph looks like, what am I going to suggest we do? XY chart, right? So, let's start with an XY chart. Notice we've kind of got a basic one to start with it being y equals 2 to the x. Because I want to show you, and we won't always do this much, well, what values are you going to tell me to use? Okay, 0, 1, 2. We need to go negatives 2. And I'm actually, for this particular graph, going to take us out to the 3s. So we're going to look at negative 3, negative 2, negative 1, 0, 1, 2, and positive 3. I'll be honest, more often than not, I just do negative 2 to positive 2. But this is our starter example, and it's a good one to look at 3. Now, the graph, the equation, if you recall, is y equals 2 to the x. I'm going to be nice to you for a moment. Because you're probably thinking negatives in the exponent, yuck. So let's start down at the bottom of the chart. Let's work our way into the more difficult ones. Sound good? If we have 3, when you put 3 in for x, what's our output? 8, because 2 to the third is 8. That was doable, right? Okay. What happens when we put in 2? 2 to the second is 4. What happens when we put in 1? 2 to the first is 2. What happens when we put in 0? 1. Anything raised to the 0 power is always 1. And if you forget that, will your calculator verify that for you? Yes, your calculator will verify that for you, right? Okay, now, 2 to the negative 1, but without using a calculator. It's going to make your brains work. No? Get the wrong answer out of the way, all right? Okay, so 2 to the negative first is not negative 2. That's the normal wrong answer. So we can stick that out, okay? Negative exponents. How do we work with negative exponents? Make it a fraction? Yeah, move it to the denominator. So 2 to the negative 1, to make it a positive fraction, that 2 to the negative 1 becomes 2 to the positive 1 in the denominator. And what goes on top? Just a 1. So what is 1 over 2 to the first? 1/2. Now, those of you that had already used your calculator, you got the answer of 0.5. Is that equivalent? It is. Okay? And I'm not saying you totally can't use your calculators, but I'm your math teacher. I'm also going to say that there is good in knowing how to do this without a calculator. Okay? So, reminding you of the skills. Okay, so you know how to do negative 2 without a calculator? 2 to the negative 2 How am I going to rewrite that? Yeah, 1 over 2 to the second. And what is 1 over 2 to the second? 1/4. What about 2 to the negative third? Officially, it's 1 over 2 to the third, which is 1/8. Notice in this situation, it's just the reciprocals of the positive values, right? Okay, shall we graph it? Let's graph this and see what it looks like. -3, 1/8. How do I graph -3, 1/8? I'm going to go left 3 and up 1/8 of a box. Left 3 and up 1/8 of a box. So I am barely off the x-axis, right? Okay, -2, 1/4. So we're going to go left 2 and up 1/4 of a box. So up a teensy bit more. It's not really visible here, okay? What about -1, 1/2? Left 1 and up 1/2 of a box. So each point has gotten a teensy bit higher, right? Technically. I'm not saying your paper shows that, but. Okay, 0, 1. Left to right, 0, up 1. 1, 2. Right 1, up 2. 2, 4. Right 2, up 4. And 3, 8. Right 3, up 8. Do you see the curve happening there? It's gradually going up on the left, and then once the numbers start getting bigger, it gets exponentially bigger. Now, this graph, along the left side, is this graph going to cross the x-axis?
No.
And the answer is no. It gets closer as your graph goes off to the left. Your graph is getting closer and closer and closer to the x-axis, infinitely so, but will never ever cross the x-axis or touch it. Technically, mine looks like it's touching, but the idea is that that x-axis is acting like an asymptote. Do you remember the word asymptote? Have we not done asymptotes yet this year? Okay, that must be next chapter then. Okay, an asymptote is a line, kind of an invisible line. In this case, it happens to be the x-axis that your graph gets closer and closer and closer to, but never crosses. And that's what the x-axis is acting as there. Okay? So when I see you draw a graph, I'm going to be looking, can I tell that you weren't trying to cross the x-axis, right? Obviously, mine ends up touching it, but... Okay. All of our exponential graphs are going to have this shape. There's going to be some line or axis they're going to run along, and then they're going to curve, and they're going to go up. Okay? A traditional graph is going to cross through 0, 1 usually. However, if you put a translation of something, on this, it might not cross through 0, 1.
This is just still all the standard translation rules.
Uh-huh. Yep. Yep, we will still talk. In fact, hold that thought for lesson 7 too. We'll talk about translation rules again this year. Tomorrow. Okay, so B. If you're ready, that is. Y equals 1/3 to the x. So the difference now, our base is a fraction. Okay. And because there's a 3 involved, I'm not going to go as big on our XY chart. We're still going to talk XY chart. But on the XY chart, I'm just going to go -2 to +2. Not that we couldn't, but 3 to the third puts you at 27 and off the graph big time. So -2, -1, 0, 1, and 2. I'll zoom in on this part so you guys can see this part for right now. And this is 1/3 to the x is what I'm doing, right? Okay, it's a fraction, so you guys are going to complain wherever I start, but at least you're going to complain in your heads. Let's still start down at the positives, okay? So if we start down here at 2, we're doing 1/3 raised to the power of 2, yes? It's a fraction, but don't make it bad. What's 1/3 raised to the second? 1/9? Because it would officially be what? 1/3 times 1/3. So you square the 1, you square the 3, you're at 1/9. That wasn't bad, was it? Point is, fractions aren't always horrible. Okay, what about 1/3 to the first? What about 1/3 to the 0? Anything raised to 0 is 1. Okay, 1/3 to the negative first. Thoughts? Carter?
Will it maybe do the opposite of what the whole number did on the other side? How like the negatives turn the whole numbers into fractions, will turn the fractions into whole numbers?
Okay, so it is, because we have a 1 on top, it is going to take this fraction, turn it into a whole number. Essentially, we're going to do the reciprocal, right? Because a negative takes whatever is, if you're trying to get rid of a negative exponent over here, it took, if you think of this 2, it was like 2 over 1, right? When we flip it, it becomes 1 over 2. So what's it do to 1 over 3? Makes it 3 over 1 raised to the power of positive 1. Well, 3 over 1 is just the whole number 3, and 3 to the first is 3. So what about 1/3 to the negative second then? What's that going to be? 9, because it's going to become 3 over 1 to the positive second. And 3 squared is 9. Okay? And yes, if you know how to use your calculator to enter these, your calculator will give you the same answers. So I encourage you to try and do the math without the calculator, but your calculator can still help you check. Okay, have you graphed this? Excuse me. Negative 2, 9 means I'm going to do what? Yeah, left 2, up 9. Negative 1, 3. Left 1, up 3. There's that 0, 1 again. 1, 1/3. Right 1. Up 1/3 of a box, if you can make such a thing happen. 2, 1/9. Right 2 and up 1/9 of a box. So technically up a little less even. What do you notice about this graph? Okay, again, it's not going to cross the x-axis, right? It's going to run alongside the x-axis. Guess what? Getting closer and closer and closer, but never touching it. My graph is backwards, isn't it? Okay. Officially, this is a reflection is what it is. We did this as 1/3 to the x is what it was given. You could also think of this as 3 to the negative x, because 1/3, if you take a negative exponent, makes it 3 to the negative x. And so it's the same thing there. So whether you see a whole number to a negative, or a fraction to a positive, or to just a regular x, it will take the graph and flip it across the y-axis. Yes?
You know our math Excel would be multiple choice. Or if we have to like actually graph it like
I feel like there's multiple choice on Math Excel. I'll be honest, I set this assignment up a week and a half ago, and so I haven't been back in, I didn't go back in to look at it this morning, but I feel like you're going to see multiple choice on the graphs possibly. So it'll be more about getting the right direction and stuff, but I can't guarantee that. Did I answer your question?
No. So the first one, did you say it was a translation? And then the second one was a reflection?
Your first one is more your original one.
Okay.
I talked about the fact that tomorrow we'll see translations, and then they won't necessarily cross through that 0-1. But this one is just a reflection. And today we're not officially calling it a reflection. We're just practicing what these look like and whatnot. But I'm also trying to make that connection that it is a reflection. I want you to realize that as well. Okay? Now, what do you notice on C? Okay, order of operations. What I hear over here? Yeah, there's a 2 outside the parentheses. If we talk about our various transformations, what is that multiplying by a 2 out front going to cause this graph to do? Stretch. Multiplying by a number greater than 1 is a vertical stretch. Okay. So this is going to be a vertical stretch. Now, for the process of our XY chart, I'm going to use that same -2 to +2. And I will say the key thing is to make sure you follow order of operations. This is 2 times 3 to the x. So, not that you have to, but I'm going to start down at the positives again. So if we do 2 times 3 to the +2 is my x value. Mathematically, how does this have to work? What's first? 3 to the second is 9. And then 9 times 2 is 18. Yes, it's going to be a little off the graph. Sorry. Okay. What can you not do here? You cannot say 2 times 3 is 6 and 6 squared is 36. Sorry. Order of operations. Okay, put in the 1. 2 times 3 to the first. 3 to the first is 3 times 2 is 6. 2 times 3 to the 0. Okay, 3 to the 0 is 1, because anything raised to 0 is 1. But then in this case, we have to multiply by the 2, which makes it 2. Okay, you ready for the fraction? 2 times 3 to the negative first. What is 3 to the negative first? 1 over 3, 1/3. So now it becomes 2 times 1 over 3. Well, what is 2 as a fraction? 2 over 1 times 1 over 3 is 2/3. So this is one where you can't just flip what we got at the bottom of our XY chart. Okay, 2 times 3 to the negative second. So 3 to the negative second. And for the sake of what we're doing, I'm going to write 1 over 3 squared for the moment, right? In case anyone's forgotten where that goes. Comes 1 over 3 to the positive second. But we know 1 over 3 to the positive second is 1/9. And then 1/9 times 2 over 1. 2 over 9.
Wait a minute, is it? Is that just coincidence?
Well, I mean, up here, 3 to the first, 3 to the second, those are your denominators multiplied by 2 on top. Down here, it was 3 to the first, and you multiply that number by 2. 3 to the second, multiply that number by 2. I mean, there's definitely patterns there. Okay, graph it. -2, 2 ninths is left 2 and up 2 ninths. 2 ninths of a box, that is, right? So something that I cannot really make happen with my ink pen. -1, 2/3. Left 1 and up 2/3 of a box. 0, 2. That vertical stretch means I no longer go through 0, 1, right? 1, 6, so right 1, up 6, and 2, 18, right 2, and up 18. So mine is way up there. Just kind of counting up and approximating. Notice again, my graph still does not cross the x-axis. And what did that stretch make this do? It made it go up steeper, quicker, right? It wasn't, as gradual. It was more quickly up. Okay. So exponential functions, good ones to know the graphs of. Questions before I move on? Okay, well, exponential functions, or graphs, lead right into your science topic of exponential growth and decay. You've done that in science somewhere along the line, I'm guessing. And so, all of these functions that we just talked about were always of the form y equals a times b to the x. The first two were just b to the x. The second one had an a, or an a value other than 1. So a times b to the x. A is what we call the initial value. Okay, so your initial value, your starting value. If you want a little helpful hint, A is also your y-intercept. And when I say y-intercept, I mean the place your graph crosses the y-axis, right? Okay. B is your rate of change. If that b value, and when I talk about b value, the b value is the value that's raised to an exponent, right? If the b value is greater than 1, then notice the function represents exponential growth. So if your base value, and this is assuming you're raised to just a regular x to the first, regular x. If your base value is greater than 1, it's going to be growth. Because what happened on examples A and C up above? My graph started gradually and then it went up, yes? A and C are examples of exponential growth. If the b value is between 0 and 1, so when we talk about a b value being between 0 and 1, I'm basically talking fractions and decimals, right? Well, notice what happened on b. My graph didn't go up, it went down. That is an example of exponential decay. The value is getting infinitely smaller. You've talked about this in science at some point? Maybe? Okay. Domain. Well, think about those graphs. These graphs go where? Infinitely left and infinitely right. So your domain is going to be all real numbers here. Because we can put in any x value we want. I mentioned the word asymptote earlier. And on these that we were talking about, our asymptote was the x-axis, right? What's another name for the x-axis? And that is y equals 0. Okay, so as long as it's not translate up or down, that x-axis is the asymptote. And the range. Well, what do you know about all these graphs? They were all where? Above the x-axis, right? What kind of y values are above the x-axis? Positive y values. Or in other words, y greater than 0. Okay? Looking at example 2. You'll enjoy these. And if I say that, that means I'm saying they're easy, right? Identify each function or situation as an example of exponential growth or decay, and what is the y-intercept? So example A, y equals 12 times 95 hundredths to the x. Is this an example of growth or decay? Why decay, Cyrus?
Because the B value is less.
Okay. The b value is less than 1. And the b value is what's ever raised to the x, correct? So that b value, I'm going to write 0 to 1 as in it's between 0 to 1. But we know what she meant, right? And so because it's between 0 to 1, this is an example of exponential decay. We were also asked for a y-intercept. What's our y-intercept? Okay, and I think Carter said a at first. It is. It's the a value, right? Where do we find our a value? Out front. Now, I personally don't care if you tell me the y-intercept is 12, using those words. I have an ordered pair written in my notes, which means if I wrote an ordered pair in my notes, that's probably my reminder to myself that Math Excel might ask you for an ordered pair, right? So what is a y-intercept of 12 as an ordered pair? 0, 12, right? Because on the y-axis, you would go left to right 0 and up 12. So a y-intercept is always going to be 0, comma, the y value. Was I correct? Do you like that problem? It's not too bad. At least I don't think it's too bad. Okay, so B. Unless you guys had questions. 25 hundredths, y equals 25 hundredths times 2 to the x. Growth or decay? Why growth? Okay, 2 is greater than 1. So that makes this growth. Y-intercept? Okay. Y-intercept is 0.25. What is that as an ordered pair if you have to give it as an ordered pair? 0, comma, 0.25. Okay, C. Sorry, you have to put your reading brains on for a moment. You put $1,000 into a college savings account for 4 years. The account pays 5% interest annually. Growth or decay? If they're paying you 5% interest, your money is growing, right? And so, that's where I said you have to read. Sorry. Sorry, not sorry, I should say. So that's growth. Okay? The question asks for y-intercept. But we don't have an equation. Doesn't mean we don't know it. Thoughts? Why 1,000?
That's the only other number.
Yeah.
What can I say?
Because it's the initial
I put my math in.
amount
Okay.
that you put in.
You can't say it's the only other number, though, because there's a 5 in there.
Other than 5, it's
Okay.
the only number.
Okay, but I heard someone,
That you put into the account.
okay, up there when we, next, where did I write y-intercept next to, or up above? Where it says A is the initial value. What was the initial value in the account? $1,000. So my y-intercept is also my starting value. So $1,000. Oops. Okay, so that's doable, yes? Real quick. Oh,
Just for the sake of it, what would the formula be?
we'll talk about that on the backside.
It'd be like y equals.
It'd be y equals 1,000 times 1.05 to the x. But again, we'll talk about that on the backside. In fact, yeah, a very similar problem in example 3. Okay, real quick. I'm not going to write all the information out. D, growth or decay? Growth because? Because 4 is greater than 1. Y-intercept? 0.3 because the A value is 3. Okay, E, growth or decay? Decay because that 0.75 is less than 1. It's between 0 and 1. Y-intercept? The 11, so 0, 11. And F. This time you put $2,000 in a college savings account for 4 years. The account pays 6% interest annually. Growth or decay? Growth. Okay, you're putting money in, they're paying you interest. That better be growth. Initial value? Or excuse me, Y-intercept? 2,000, which is your initial value. Okay. See if I can get through enough of what I want to on the back. Might be a little short on time here. We'll see. I did not have plans to do every example on the back. I was going to kind of do some hit and skip. So we'll see if I get through, because my plan was to be done with this lesson today. Which, yes, did you hear that? If I'm done with this lesson today, that means lesson 7.1 in Math Excel is due when? Tomorrow. Crazy thought. A regular scheduled math is just a crazy thought in my mind right now, but okay. So exponential growth and decay. We talked about on the front side, y equals a times b to the x. Well, we've got another variation of that. And this is more the one you use if you're trying to come up with your equation. When Ethan asked me for an equation on that last one, this is essentially what I used. So a of t equals a times 1 plus r to the t. And you'll notice there it says if r is positive, then this represents exponential growth. If r is negative, then this represents exponential decay. Okay? Now, if you are asked about a growth or decay factor, that is represented by the 1 plus r. That is your growth or decay factor, is that 1 plus r there. Now, let's start with some pieces. Because if we're going to use this equation, it helps if you know what each of those variables stand for, correct? What's that a going to stand for, you think? Initial value. What was a on the other side, right? A is initial value. So I'm just going to write this information off to the side here. A is initial value. Let's get the obvious t out of the way. T is usually time. The other big one that leaves, R. What's R usually stand for in these types of formulas? The rate. Okay, so the percentage rate, essentially. And when we talk about the percentage rate, remember when you put the percentage rate in an equation, we're always going to put it in its decimal form. Okay, you're always going to be putting it in its decimal form.
So you become less than things. It's like 100 times 25%.
No.
Okay.
I don't ever teach you using the percent button on a calculator, ever.
I mean,
We need to know, because as a math teacher, you need to know how percents work. So, okay. The one other thing on here, A of t. A of t is what this equation equals, right? And so it is your total amount after t years. Now, I'm going to use a different word though. I'm going to say it's the balance after t years.
Couldn't this also be represented as f(x)?
It could. We don't usually use f of x here, but always. Okay, so A of t is the balance after t years. Okay, with that in mind, let's try the first example here. Example 3. It says you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years?
That's right.
Now, I'm going to suggest we write an equation for this. Okay, that's an important thing, that we can write an equation for this situation. What's our equation going to model? Well, we're going to use that A of t equals A times 1 plus R to the power of t. That's what our equation is going to model. Now, we have to identify the pieces to this equation, don't we? What do you know that we can fill into this equation? 1,000. What is the 1,000? That's your initial value. So 1,000 is going to go in for A. What else do you know? 6 years. What's 6 go in for? 6 years is time. So we're going to put 6 in for T.
Wouldn't you put 0.05 in for r?
What do you think? 0.05 for R?
Yeah, because 5% of the.
Okay. So 5% is our rate. It is our percentage rate. But as I said, we don't put 5% into an equation format. And so in order to change a percent to a decimal, move the decimal 2 places left or divide by 100. And that is 0.05. Now, is this going to be a growth or decay situation? This is going to be growth, isn't it? And the key to watch here, I ask that because that's going to tell me that we're going to have to add our 0.05 in the equation. If it was decay, we'd want to be subtracting. But because it's growth, we're going to add it. So, fill in our equation. A of t, so I'm really going to write this as A of, what are we trying to find? 6. We're not going to do anything with that 6. We're trying to find the amount in the account after 6 years. So, what's little a? 1,000. 1. What do I do for plus R? Plus 0.05 raised to the power of 6. Okay, a little basic cleanup. 1,000 is 1,000. What's 1 plus 0.05? 1.05. Yes, it is that basic. Now, this is where your homework requires the use of a calculator. Make sure you know how to plug this in on your calculator. Me personally, I'm just going to do 1,000 times 1.05 exponent 6. You'll have to practice on your calculator to make sure you know what you're doing there, right? Every calculator is a little bit different, and we can definitely work on that tomorrow. I had 1340.095641. Is that the kind of answer I want?
No, it's doing they went around is like 10 cents.
what kind of answer do I want? This is what kind of answer? Money. Money always goes how many decimal places? 2 decimal places unless told otherwise. I don't want the nearest dollar. I don't want the nearest dime. I want the nearest penny. So, to the nearest penny, this is going to be $1,340 and 5 tells a 9 to go up to 10, so 10 cents in this case. Okay, so my point in saying that, I want it to go to the nearest penny, 2 decimal places. It happens to be 10 cents in this case. Yes?
This seems logical, but like, wouldn't it round down so people, so like the banks are always like so stingy and like if it's point something they'll round it down?
Technically, though, if that next digit is above 5, even banks round up, I believe.
Really?
I think. Don't quote me on that, but. Okay, guys. Listen real quick. I did not quite get through as much as I feel is necessary, so I will finish a few more examples tomorrow. Maybe not all of them, but I will finish some examples, which means you won't have to have the homework done for tomorrow.
Oh, no.